Okay, let's get started, everyone. Good morning. Any issues with the lab? So remember, the lab's due Friday. There's no late penalty for weekend days, so if you turn in Sunday, then that's fine too. But officially, it's due Friday. And remember, it's based on when you upload your lab on Dropbox. We have a pack for this one, right? Yeah. If you run the script CSCE, grade.sc pack, it'll package your project into a form that you can just upload it into Moodle. Or at least it should. If you have any issues, let me know. And then we have a quiz also that's second quiz, actually. Second quiz? Yeah, second quiz. Sorry, I'm teaching two classes this semester. I'm getting confused. So we have a second quiz that's also due on Friday. That one, though, the cutoff is Friday. So you got to that's kind of confusing. Yeah, you want to take the quiz by Friday, but you don't technically have to turn in the lab until Sunday. Make sense? Okay. All right, so in this next phase of the course, we're gonna start building systems on the FPGA boards. They're the same boards that you've already used in 611 and 313. All of you have taken 611 and 313? Hey, good. So we're going to basically combine those two things. As I explained last time, we want to be able to add our own IP blocks to the platform design, FPGA platform design. So I'm going to very quickly run through a review of basically 611 and 313. If you have any questions, let me know. I'm going to go real fast, though, just to make sure everyone's on the same page. So we're going to be using field programmable gate arrays. They're electronically configured chips, so they're basically a paperweight when you power them up, but then you configure them and they will begin to behave as though you had fabricated a chip, right, with the circuit. The downside is it's 10 times slower than if you had fabricated the chip, and there's 10 times less capacity because of the fact that the reprogrammable gates have to be spaced out more. They're less dense as compared to an application-specific integrated circuit, right? Okay, so we're going to use these boards. You'll notice that when you power these boards on, they actually do come in. They start doing stuff. This is the FPGA that's driving this blinking lights. And the reason that happens when you turn it on is because there's a flash chip on the board that configures the FPGA on power up. You can actually reprogram that flash directly from Quartus, although it's best that you didn't, because I don't know how to restore the original configuration to that thing. And what may happen is if you program it with a bit stream that doesn't do anything obvious, then someone will turn the board on, it won't start blinking, they'll think the board is bad, right? Even though it's not, it's just hasn't been programmed with that configuration. Okay, so the FPGA is blank initially, and then you have to design it. In this class, we're going to be using Platform Designer that you used in 313, and we're going to build this really large kind of complex system that includes a soft core processor, which is essentially a stand-in for like an Arduino or a Teensy processor. It's more powerful than an Arduino, 8-bit Arduino, but less powerful than like a RISC-based, not RISC, sorry, ARM-based processor that you have like in a Raspberry Pi Pico. And part of the reason is because it's a 32-bit processor, but it's a soft core processor, right? Meaning that it's not transistorized. It's not built with transistors. It's built with LUTs, right? FPGA LUTs, FPGA gates. So it's gonna be 10 times slower. In fact, ours is more than 10 times slower because we're only going to run ours at 50 megahertz. You guys with me? Now you might ask, how fast could that processor run? Maybe 150, 200 if we tried. Okay. Now you may also ask, wait a minute, why go through all the trouble? I mean, you can buy an off-the-shelf Raspberry Pi Pico or Teensy or Arduino or BeagleBone, or there's a lot of chips that you can buy that are designed for the types of stuff we're going to do in this class, which is like basically control things, control, I don't know what you call it, small equipment, control small objects, systems, vehicles, whatever. So why go through all the trouble of configuring an FPGA? Well, we're doing it in this class because it's for teaching purposes, so you can understand how those chips work, essentially, right? So we're making the process by which we build these systems a little bit more complicated than it might be in practice if you just bought a chip off the shelf. But this way we get to see what's under the hood, get to understand how the thing works under the hood, okay? Because most embedded systems are set up in a similar way. Okay, so that's the board. You guys are familiar with that. You guys know Quartus, Platform Designer. Now, one thing is when Rasha teaches 313, so I developed 313 originally, and Rasha, who was my former student who TA'd it with me, when she became an instructor, she took over teaching. However, I think she resisted one of the changes I made in 313, which was to move away from Eclipse. Did you guys use Eclipse? Yeah, so that was like 90% of the class, right? Was, because you just design the hardware up front, you put it on there, and then you typically don't change the hardware much. Most of 313 is programming in Eclipse with C, right? And that's really the point of it. It's an embedded systems programming course. That 313 doesn't emphasize the hardware that much. That's what 611 is for, right? But when you guys use Eclipse, I don't know if you know, well, I'm sure you noticed this, but sometimes you hit download and it's like, nope. And you're like, why? I'm like, just no. And it does that a lot. Unclear why, right? And then sometimes, I don't know if you've had this happen, and I never did figure this out, but the last project of 313, at least my 313 course, was to develop a 4-core Neos processor and use all 4 cores to render a Mandelbrot fractal on a monitor in real time, or in real time in the sense that you're watching it render, and then you're supposed to visually see the rendering speed change as you add cores, right? Or make optimizations to your code or your hardware, right? That was the idea with the final project. I don't know if you guys still do that?
Like an image where we have to rotate it.
Okay, that used to be like lab 2 when I taught it. I think she slowed it down. That's fine. That always happens though. It's typical. But anyway, my point is when we went to the 4-core processor, you would have to basically have 4 Eclipse projects, because there's no operating system. So whenever you link your binary file that you download to the processors, they would have to be linked for the specific memory regions that each processor would occupy. Otherwise, they'd step on each other, right? So you had to have 4 ELF files, 4 binary executable files that you would then offload to all 4 processors. Because that's, unfortunately, in bare metal, that's the only way to do multi-core. Like the only other way to do multi-core where it's more transparent is if you have an operating system that's multi-core aware, that has a scheduler that can dispatch and load balance the processors dynamically. But in a bare metal system with no OS, there's no operating system. You basically have to run separate programs on separate CPUs, and each program has to use a different memory address, because there's no memory management unit, there's no virtual addresses either, so it's all physical addressing, right? Okay, anyway, my point is that whenever we did that, Eclipse would often corrupt the workspace, and you couldn't you were dead in the water. There was no downloading anymore at all. The only way to fix that problem was to reset the Eclipse workspace, which then meant you had to import all 8 projects manually. 8 projects were the 8 projects and the 8 BSPs, right? So that was awful, and that was why I said no more Eclipse. This is terrible. So I went to command line tools. And so Intel has a set of command line tools as an alternative to Eclipse. Now the difference there is that Eclipse doesn't have make files, right? So Eclipse basically constructs the make files based on the project that you've set up. Whereas if you go command line, you're now doing make files. You're just using the make, essentially, right? So I'm going to show you how to do that. I'll give you a tutorial of that. And again, the reason we did it was not just because of the making, but the downloading and the debugging was much faster and way more reliable if you use command line, because their Eclipse add-ons that enabled the debugging and downloading of code to the boards it's not usable in my opinion. Okay, and you might say, why don't you just upgrade the version? Surely they fixed it in the later versions of Quartus. Yes, but then they stopped supporting the FPGA. Our boards are a little too old for that, so we're kind of locked in at Quartus, I think 18. I don't know if we can move up to 19 or not. I don't know if I've tried that, but I think we did try it, but we couldn't because for whatever, there is a reason we're stuck at Quartus 18. Okay, anyway. All right, so let's see. Blah, 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 blah. So you guys, your environments, this slide says set up your environment, but it's blank. It just says run Quartus. And the reason for that is because Ryan, the IT guy for the department, basically forces you, when you log in, inside the system bash RC file, it'll load the environment for you. So you don't have to worry about anything. You should be able to open up a window or terminal and launch Quartus. You see that. Then you want to create a new project. Now we're still using Quartus for projects. So you'll set it up the same way you did in 3.13 and 6.11. Let me clarify that too. So if you've recently taken 6.11, we changed this too, where Charles basically scripted out all this stuff for 6.11, right? So instead of creating a new project, we just gave you the project file and you just run a script to deploy and test your code on the FPGA board. In this class, we're going to go back to the 3.13 way and just have you create a new Quartus project manually. You can name it Lights if you want. That's usually our initial project name. And then you have to select the right FPGA. For some reason, there's 8 million different FPGAs that you can choose from. Unclear why. So you have to search a very long list to look up EP4CE 115 F29C7. 115 means 115,000 logic gates. EP4 means Cyclone 4. That's the generation of the FPGA. F29 refers to the package that it's in, that ceramic black thing you see on the circuit board. And C7 refers to the speed grade. Some FPGAs just work faster than others, and so they're grouped by speed grade. Okay, so you click Finish on that, and then you have to download the pin mappings. So you have to import this pin mappings file. You guys know what the pin mappings does? So that's what associates top-level pin names to actual numerical pins, right? So the FPGA is on a BGA, a ball grid array, and so the rows are, I think the rows are numbers and the columns are letters, so it's like an Excel spreadsheet. And then the pin mapping file is what maps each of those, like pin, like C17, for instance, to a name, which might be RGB red 6, right? So in order to use symbolic top-level I/O pins that correspond to pins on the FPGA and thus devices on the board, you need that pin mappings file, okay? And then you can also download lights.sv. Hopefully that's on Dropbox. If not, I'll add it. Lights.sv is the top-level design that we used to just give you in 3.13 because you couldn't write that yourself because you hadn't taken 6.11 yet, because we don't sequence 6.11 and 3.13, right? Now in this class we do, so you would have had to taken them both, but I'm just still going to give you the top-level file for that. You can, of course, add to it if you want or modify it. So you import that, and then set lights.sv as the top-level entity, and then you open Platform Designer, okay? So once you get in there, you get that window. So I've actually, I've got it open here. So in this class, we just set up kind of a minimal design. It doesn't have to be as many things as you had in the 3.13. I mean, we'll add to it, but at a minimum, you need this clock source. You guys remember this clock source thing? So this is a little confusing, in my opinion, because the clock source doesn't really do anything. It doesn't really correspond to any hardware. All it does is add a pin to the module that gets generated from Platform Designer. It adds a clock pin. And then you have to then take that clock pin and you have to then connect it to another module that's called a phase lock loop. It's an analog circuit that takes a reference clock as an input, and then it can multiply the frequency and divide the frequency and change the phase shift, right, of that clock. And that's what we need. And it cleans it up too, because the input clock is coming straight in from a piezoelectric crystal. So on the board, there's a crystal, and crystals are pretty easily recognizable because they always, for whatever reason, they're always housed in a like an aluminum or silver colored chip. Don't know why, but they always are. All the crystals or all the crystal oscillators they're always, all the chips on this board are black, except a few, 3 or 4, all black chips, but 4 silver chips. Those silver chips are the crystals. And inside, and it's also shown on the silk screen. The silk screen is where they write stuff on the circuit board. It says 50 megahertz, right? But the problem is that the crystals don't produce a very clean clock signal. It's jittery, which means that if you measure the frequency changes. It changes over time. It's not exactly 50 megahertz. So you bring that clock signal into a phase lock loop, and that circuit will clean up the clock, and it also allows you to like double it or triple it, right? So if I wanted to run the Neos processor at 200 megahertz, all I'd have to do is tell the phase lock loop to multiply that by 4. And now I've got a 200, of course, that's assuming, of course, the processor is capable of running at 200 megahertz, right? But changing the clock speed is easy. Phase lock loop makes that real easy. You can multiply and divide. Now on this board, the other thing that's confusing, and I don't understand this either, by the way, we run the clock at 50 megahertz, so the phase lock loop actually doesn't multiply or divide, it just cleans up the clock. And then we run the processor at 50 megahertz, and we run the memory, the SDRAM at 50 megahertz, which is kind of weird because in most computers, the core clock speed of the CPU is usually much faster than the memory clock, right? Because CPUs run faster than memory, right? The memory clock is slower because that clock goes out into the memory, and the wires that go to the memory from the CPU are long wires, and the longer the wires, the more capacitance and resistance they have, and the longer it takes to charge and discharge those wires, right? That's the RC constant, right? But on this board, they're the same because we're not being very aggressive with our clock speeds here. But they have to be out of phase. And I don't understand why. No idea. But if you have the memory in phase, the memory clock in phase with the CPU clock, it works, but you get intermittent glitches. And I never could figure out why that's the case. So the clocks component on here, which is the phase lock loop, spits out 2 clocks. They're both the same speed, but they have different phases. And one of them is used to power the internal things inside your design, your CPU and all your stuff. The other one is then exported to the SDRAM using another one of these clock sources. So one of these clock sources is your input pin. The other one is an output pin to the SDRAM. And I know that's wildly confusing, and believe me, it took us a while to figure that out as well. Unclear why you have to do that, but that's part of why we have so many modules. Okay, so we've got a clock input here, and notice it says over here in this column that it's exported, so that's what actually creates the physical input pin. But then we have the internal routing. Okay, oh, we also have a reset here that should also be exported, and it is. Yeah, so we got a clock input and a reset input. So if I were to generate this thing right now, I think it would only give us those 2 pins. So if you look at if you guys can read this, it's probably too small. Let's zoom in here a bit. So if you look at the lights, sorry, actually it should be this. If you look at this, this is where we instance the Neos system as a module in the top level, basically the top level design. So we're instancing Neos system where we're calling it U0 for some reason. I think because that's the nomenclature they use for circuit boards. They call components U and a number. But right now, it would only have this clock and that reset input. So we would connect the clock input on the system to clock 50, which is our actual top level pin, right? And then key 0, which is the rightmost button, is our reset button. Reset is typically connected to a physical button, even to this day on modern computers. Like even on these computers, there's a reset pin going to the CPU, and it's wired directly from the button, because that's the only way to really do a reset. Okay? But none of these things would show up. All of these wouldn't exist because we haven't added any other components with exported stuff in them, right? All these come from the SDRAM controller. Okay? Now, one thing you might notice, well, I'll come back to, oh, and there's the SDRAM clock, by the way. So these guys are all coming from the SDRAM controller, and this guy is coming from the second clock source that we're going to add, okay? You might say, well, why don't they just export the clock directly from the controller? Well, they can't, because the controller, it doesn't have, I don't think it has the clock, or maybe it does, but I don't know. I don't know why we have to do it that way. Very confusing. Okay, so I've added all these things. So we have we've got the clock source, that was in there by default. We got the NEOS processor, the PLL, the SDRAM controller, and there's the second clock source for kicking the SDRAM clock out, and the JTAG UART. You know, you'll say, wait a minute, hold on, why doesn't the JTAG UART have any pins exported? Where are those pins at? Why aren't they there? I don't see any UART pins coming out of this thing. There's no UART pins. You guys know about UART now. It should be like 2 pins, right? A receive and a send. They're not here. Why? Because it's a JTAG UART. So JTAG is, we talked about the JTAG protocol, but we didn't talk about how it relates to the FPGAs. On an FPGA, JTAG is a side channel. It is not going through pins that you can access. They're magical invisible pins that are connected to the boundary scan network inside the CPU. And the boundary scan is just there. It's hard logic. It's not soft logic. It's not FPGA. It's not logic you can touch or even see, because it's built into the fabric of the FPGA. There's a JTAG chain that worms its way all throughout the FPGA, and the JTAG UART that you add in the design hooks into that chain. And so remember we talked about how JTAG has different instructions, right? So there's different instructions that you can load into the address register in JTAG. That UART carries the UART through that JTAG instruction somehow. Again, I don't know exactly how that works, but JTAG is, it has the ability to test the FPGA, to configure the FPGA, to put the bit stream in, to pull out certain registers, and UART. It carries the UART signal on top of the JTAG bus, and then ultimately through the USB bus back to the computer. So it's actually UART operating over top of JTAG, operating over top of USB. Right? So there's no pins for that. That's just, you just get that for free somehow. Okay, but normally anything you add in there that requires I/O would have a pin there, just not JTAG. Okay, okay, that's it. So I haven't connected these guys, and this is the hard part. So basically, the first thing you can take care of here, and by the way, these are your connections. This is really hard to use, but believe me, there's no really better alternative to this, unfortunately. Xilinx, which is the other company, now AMD, AMD bought them. The other big FPGA company, Xilinx/AMD, AMD/Xilinx, they have a tool called Vivado that's similar to this, and instead of doing it this way, they actually have you put a block diagram, right? And so instead of having it columnar like this, it's like blocks, but it's not really any better, because then you're still having to draw these wires, except instead of filling in buttons, you're actually drawing wires, and it turns into a big rat's nest even then, right? So it's not, I don't think that is any better. I actually prefer this way of doing it, even though either way, the connections can become overwhelmingly complex. Okay, so we've got the clock output. Now you might say, so we've got this, like I said, this does nothing. All it does is connect that input pin to this internal clock network, right? So all I got to do then is connect that clock to the clock input of my processor, which you just do that. You click the button, and that clock, oh, sorry, wrong. Sorry, it has to go to the PLL first, sorry. I don't want to do that. I want to connect this clock to the input of the clocks component. There we go. Okay, you see that? And then this thing is the PLL that's going to clean up and filter that clock, and it has an output called sysclock. That's what I'm going to connect to the processor clock. And why does it keep undoing that? Click. There we go. Oh, I guess it's just lagging. Okay, so we got a clock there. The SDRAM controller is going to use another clock That's the SD-RAM clock. So I'm going to connect the SD-RAM clock to that clock. Okay, and then that SD-RAM clock is going to connect to the clock in on this other clock source. And then I'm going to have a clock out, which I'm going to export as SD-RAM clock. Okay, now this, by the way, you guys, I want to make sure everyone understands this because we're going to start adding our own components in here. So it's more important that this part be clear than it was in 3.13. Okay, so then we got a UART, and UART's going to use the sys clock. So I'm going to connect it. I already forget which one of these, so I have to, there we go. That's the sys clock. And then let's do the reset. So there's our reset. I'm going to connect the resets to all the resets. So reset of the NEOS, reset to the what is that, the PLL? I don't know why the PLL needs a reset, but SD-RAM controller reset, and I'm not going to do that one, and the UART reset. Okay, so all my resets are connected. Okay, then I've got the processor here, and it's got a data master and an instruction master. Now, both the data master and instruction master, for some reason, have a loopback connection to this debug mem slave. Obviously, this has to do with debugging. Like, so when you launch this in GDB, it allows you to step through, which we'll use. But I don't know why this weird external loopback needs to be in there. I always just leave it alone. But we do need to connect it also to the SD-RAM because all of our SD-RAM, all of our instructions and data will live in SD-RAM. So we're going to slave the SD-RAM controller to the data master. Come on, buddy. And instruction master. So I'm going to connect both of those bubbles because both our data and instructions will live in the same place. Oh. I don't know why it keeps unclicking that. Stop. There we go. Okay. All right. Is that it? Oh, then there's an interrupt here for the UART. Let's go ahead and connect the interrupt back to the JTAG. I mean to the processor, even though we never use it. I think that's about it for the connections. I usually forget something though. Okay, but let's go ahead and double check our NEOS settings here. I think that's fine. NEOS 2F. We'll just go with that. SD-RAM, there's some settings here we need to tweak here a bit. We need to set up the SD-RAM that's on the board. So this board has 32 bits is the width of the SD-RAM. Chip select 1, banks 4. Is that right? I don't remember. It's in the slide somewhere. Yeah, here we go. Yeah, here it is. No, actually, that's not it. Here it is. 32, chip select 1, banks 4, row 13, column 10. That's row 13, column 10. So those were bits. So if you have 13 row and 10 column, that means you have 23 total bits. And this memory is 23 is 8 mega, right? 23 is 2 to the third times 2 to the 20th, right? 2 to the 20th is millions. So 8 million, right? But it's also 32 bits wide, so you have to multiply that by 8, right? So that goes, I'm sorry, no, sorry. It's 32 bits wide, so you multiply by 4, right? There's 4 bytes in 32 bits, right? So that gets you up to 32 million, right? And then there's 4 banks. So you multiply by 4, that gets you up to 128. So the 128 megabytes of RAM, which you can get by taking 2 to the power of the row bits plus column bits, right? Then you multiply that by the width, 32 bits, and then you multiply that by the number of banks. And that gets you to 128. In fact, it even calculates that for you here. If you scroll down, you can see that it actually updates this memory size based on your settings. And that board, if you look at the black chips on there, you'll see that it's 128 megabytes. That's how much memory we have. Not a lot, but okay. Anything else? I think we're done, right? Are we done? Hopefully we're done. We've got some errors here. What are the errors? Something about vectors? Yeah, reset slave is not specified. Exception slave is not specified. Okay, so we have some overlapping memories. So let's go to our address map. Okay, now remember that these connections that we're making are using the what's the name of it? Avalon bus, right? The Avalon bus, and we're going to learn about that some more. But it's similar to SPI in the sense that it's a master-slave style bus. But the difference is that Avalon is a parallel bus. So when you transfer data on Avalon, you transfer a whole word in parallel. So I think in this case, we're using a 32-bit wide Avalon bus, but you can go all the way up to like 512 or 1024. So if you have a really high-speed peripheral on here, you might have like a 512-bit wide Avalon bus, right? That's how many the data bits you can transfer in one cycle. So let's go ahead and go to System and say Assign Base Addresses to automatically assign all the base addresses. And you can see here that the SDRAM controller has an address range of 800,000 in hex up to FFF, right? So this is the same kind of range that I showed, in the first lecture, right, for the I/O ranges. Okay. Now, by the way, these are physical addresses. So when you get into GDB, when you're testing your code, all of your pointers in your code will also be in this range because it's just a physical memory address. On a real computer, on a big computer that has a virtual memory system like these ones, the physical memory addresses are actually not the same addresses as you see in your code if you're debugging it. Your code is using virtual memory addresses, which are translated by the operating system through the page table to physical addresses, which simplifies things. That way, every task, every program, every process can have its own its own range of addresses, which are then translated to physical addresses, right? But in here, everything's physical. Same thing with Arduino. In fact, any processor that doesn't have an operating system is guaranteed to have a physical address mechanism. There's only one version of Linux I've ever seen that uses physical addresses. There's a version of Linux called MuC Linux, which stands for Microcontroller Linux, and it's the only one that allows you to use physical addresses. However, the Neos processor does have a memory management unit, and you can run virtual addresses on here too. I've just never tried that. I don't know how that works. I mean, you have to run Linux obviously on it for that to make any sense. Okay. Anything else here? Still got some errors. Reset slave. Oh yeah. So if we double click on the Neos again, we have to tell the Neos what address to go to if there's a reset or an exception. Right? Vectors. Okay, so the Neos processor uses vectored exceptions, which means that if an exception occurs, which we've talked about, an exception or an interrupt, it'll go to a certain address, memory address. And if there's a reset, it'll go to a certain memory address, right? But you have to tell it. Those are hard-coded, and those are hard-coded values. Again, this is on any processor, even on these ones. They have hard-coded addresses that it'll go to when those things happen. So we're going to have to say the reset memory is the SDRAM controller, and it's going to go to address 0 on a reset, and the exception vector. By the way, exceptions, interrupts, essentially the same thing. An interrupt is the reason why they have different names. Interrupt is an external source of something happening requiring the CPU's attention, whereas an exception is an internal source, like a divide by 0 error, or invalid instruction, or memory error, something like that, right? But basically, the way that they're handled is the same. They both go to their handler, exception handler, right, that we talked about. Although interrupts are the only ones with the acknowledge, obviously, because they have to acknowledge the external device. Okay, so anyway, 20. Okay, cool. All right, I think we're good. Oh, right, and the SDRAM must be exported. Thank you for reminding me of that. So we have to go down to the SDRAM and just tell it to export its signals. as external pins, which is basically just all you have to do is click that and hit enter. Okay, that should fix that. And the final warning that we have here is the JTAG UART must be connected to an Avalon master, which means I must have forgot to do that, or I did do it and it reset it on me again. Which means I just got to go down to here and say, I got to connect. Now here's the problem. Which one do I connect? I have two potential masters for the JTAG. Well, the masters are the instruction master and the data master. Obviously, I'm not going to be fetching instructions from JTAG, right? I use the data master because, so by the way, the difference is the instruction master is used for fetching instructions, whereas the data master is used for the load and store well, technically load I/O and store I/O instructions. Remember, we talked about that when we talked about program I/O. So when the CPU fetches instructions, it has to grab those instructions from a slave. It has to pull those in. The only place it's going to do that is from like the SDRAM, right? Or like a scratch pad memory, like a little bootloader memory or something, or a ROM. Like the computers here actually have a power on self-test BIOS section, which it actually grabs, which is a ROM on the motherboard, right? I don't know if you guys have ever built a computer, but you can, if you boot up a computer with no hard drive in it, no operating system, you'll still see it printing stuff when it turns on because it's fetching instructions from a ROM that's on the motherboard before it branches to the operating system, which is on a drive, right? So you could have multiple instruction masters for that reason if you wanted to have like a boot up, bootstrappery or bootloader section in there. And that's pretty common. But in this case, we're just going to get the SDRAM, which is why I connected both of those to the SDRAM up there. But for the JTAG UART, I only need the data master. Please tell me that's the data master. Nope, wrong. Yeah, and I don't think anything bad will happen if you do connect them both. But okay, are we good now? Looks like we're good. Yeah. All right. So once you get that, you save it. Let's save as, I'll call it, what do we call this? Lights? Lights. It takes a little while to save it, and then we can generate HDL and tell it to generate Verilog, and I can't actually get to the button. I have to rescale this. Let's scale it to 125. There we go. Now I can hit generate, but now everything's smaller. Okay, so it's going to generate that, and that takes a little while. So what this is doing is generating hundreds, maybe not hundreds, maybe around 100 or so Verilog files that comprise the system. Now you might say, why would it be 100? I mean, you only got like 7 modules in there. Because most of those modules come from the Avalon bus. I'll cover this in more detail shortly, but you know how with the SPI bus, there's a direct connection between the master and slave? Well, in the Avalon bus, there isn't a direct connection. There's a bus controller. And the bus controller is what's programmed with the address map. Remember how we had the address map here? So each one of our peripherals, so the JTAG has its address range, the SDRAM has its own address range, and then there's this debug thing for some reason has an address range. I'm not sure what, again, that's part of the debug infrastructure. Everything has its own addresses. These addresses actually get programmed into the bus controller. So when the master says, I want to write to this address, it uses that address as a destination to send it to the right peripheral, right? And so that's the bus controller. And there's a lot of those bus controllers. So a lot of the Verilog files you'll see generated are from the bus infrastructure, not necessarily from, but then again, the Neos processor I think has multiple Verilog files. Of course, they're encrypted because they wouldn't want you to see their precious processor design. Okay, anyway, so I think we're good to go with that, right? It looks like it generated. Okay, then once that's done, you then go back to Quartus. Sorry, we're up here. And inside Quartus, you would just bring in your lights.v, and I think you guys should be good from that point, right? Okay, any questions about that? Okay, I just wanted to go through that demo, even though it might have been gratuitous, because I wanted to make sure I got that on the record. So, because it's easy to make a mistake. If you forget to connect something in there, you know, you might get an error or warning, but you might not, and then it's just bricked, right, on the board. Now, one thing that irritates me, maybe one of you guys can figure this out, because it's pretty common that in this class and in 611 we'll have groups that'll find things that I learned from. One of the things that the Xilinx tools offer that Intel apparently doesn't is a module that you can put in here to monitor an Avalon connection, such that when I put this on the FPGA and then open Signal Tap, you guys remember? You guys use Signal Tap? 313, 611. So Signal Tap uses JTAG, and it allows me to create virtual logic analyzers in the FPGA. Logic analyzer will, you know, after a triggering event happens, it'll capture data on every clock cycle and let me see what it is and display it in a waveform, right? So I can look at signals in Signal Tap. You have to add probes and recompile your design, but once you do that, you can actually use the computer as a logic analyzer and actually look at what's going on in the FPGA. It's pretty cool. It's not a great way to debug. It's better to debug in the simulator. But if you have a situation where the simulation worked, but the hardware doesn't, yeah, that's the only thing. Then you have to use Signal Tap, right? Simulation is supposed to match the hardware, but only in an ideal world, right? Okay, so, but the problem is that all you can pick is individual signals. It would be nice if you could put one of those Signal Tap probes on the Avalon bus. And you can do that easily in Xilinx. You just put an ILA probe in there and you can trigger on transactions, you know, bus transactions. How cool would that be? You could actually see the bus transaction. There's multiple signals that make up the bus, just like there was with SPI and I2C. But it'd be nice to watch it. But I haven't figured out a way to do that yet. I have not figured out how to monitor the buses in Signal Tap. There's got to be a way to do it. I can't believe that they just don't have the capability at all. But if you guys ever stumble upon anything like that, let me know. Okay, so let's get back to lecture here. Okay, so we added all our stuff, and so then you create the lights outer shell wrapper, which I provide to you. In Xilinx, they generate this automatically, but this is another thing Xilinx can do that Altera, Intel can't. Intel, you have to manually write that wrapper, so we just give it to you. When I say wrapper, I mean that's the top level function, but all it does is make connections between the real pins on the FPGA and the pins that are on your Neos system, right? That's all it does. That's why it's called a wrapper. It just basically consolidates the interface. That's what it looks like. Okay, so this is the part. This is the part where you guys haven't seen this yet because Rasha is using Eclipse. So, so you can program the FPGA using this command, neos2-configure, and whenever you compile your design in Quartus, it's going to give you a soft file, a serial object file. That's the bitstream file. You can program it there if you don't want to use the GUI, right? But that one's not a big deal because the GUI, the Quartus GUI isn't too bad. Okay, but then for the software part though, this is where things are different. So there are command line tools to do all of the stuff you did in Eclipse. This command here, it's a long command, but the purpose of that command is to set up your software projects. You guys remember how you had a software directory and then you had a lights and a lights BSP? The lights BSP, of course, would be generated automatically and it would be overwritten anytime you change the hardware. And the lights was the one that you were supposed to edit. The lights BSP, even though you were not supposed to change that, because any of your changes would get reverted next time you change your hardware, but it still allowed you to see what's in there and how the hardware abstraction layer worked, right? You guys with me? Like the interface to the hardware stuff. So now, if you use this command, neos2-software-example-create, you only have to run this once to set up the software. But you say --name equals lights, --sopc file equals neos system.sopc info. This is the file that's generated from the platform designer, right? This just has all the blocks that you put in that thing that we just did. --type equals hello world. This is like the template that we use that doesn't do anything. There are other templates. I haven't really explored them though. I have not on here. I've done it on the Xilinx one, but I'm actually kind of curious what other templates are available. I think one of them is a memory test, but we always use hello world. And then CPU name. Remember I said that if you have more than one CPU, you can't just, it's not like Linux that'll just use all your cores. You have to target a specific CPU. And that's why you have to say dash dash CPU name equals Neos2 underscore Gen 2 underscore 0, which refers to the CPU that you added in Platform Designer. That's the default name. If you change the name, you'll have to update that. App directory light and BSP lights, BSP directory lights.bsp. So you run that one time and it generates the software. And then you go in the lights directory and you run a script called create this app and it'll build it all outside of Eclipse. Now, if you really want to use Eclipse, I'm not gonna stop you, but this is better, in my opinion. It's more reliable. It's just a lot more typing though, because it's command line. Of course, you can write your own scripts too, but you just run that once, and then once you run that, you just type make, and it builds it. And then once it builds it, you're going to get a lights.elf. That's the output of the make process, and that's the binary file that you're going to use to download to the board. And so you can run neos2-terminal, which will open up the JTAG UART, and then you can, so anything you print from your code will show up there, and then you can download -g lights.elf, and that should download it to your board, assuming, of course, you've programmed the FPGA. Right, because otherwise the CPU won't exist. There'll be nowhere to download the thing to. Okay? Okay, now this is the part that I like, and I'll give a demo of this next class. I don't have time today. The debugger. Now, a lot of, how many of you guys, a lot of you guys use the debugger in 3.13? It's a good habit to get into, because if you're used to print debugging, which I know a lot of you guys use print debugging, I hate print debugging because you have to recompile in order to have your print statements activate, and then once you fix the bug, you have to then go back and delete all those print statements, right? So I don't like print debugging at all. Once I started using a GDB debugger, I fell in love with it. Now I need them. The problem is Arduino doesn't have one. Like if you use the Arduino IDE, no debugging. So you have to use print debugging. The problem is that if you use print debugging, you go over the JTAG UART, and if you print too much too fast, it'll overrun the buffer, because the JTAG UART is very low bandwidth, right? JTAG is like megabit, 5 megabits, right? But remember, that's the baud rate. That's not the, it's like, remember with UART, there's the baud rate and then there's the data throughput, right? JTAG might have a 5 megahertz or 5 megabit per second baud rate, but you have to deal with the overheads of going through the JTAG protocol and the UART protocol and the USB protocol. Right? And you're also routing this through soft logic that's running at 50 megahertz on the chip. So what that means is if you have a loop in your code and you put a printf in that loop, you're done. It'll brick the system, because it'll go through the loop really fast, and it'll overload the UART. It's really easy to do, and there's no warning. It doesn't gracefully, there's no graceful degradation. It just craps out and bricks your system. So and also, JTAG is slow, so it's not really practical to use print debugging on here. I think it's the same way on Arduino too, but typically programs with Arduino, you're usually not writing really complex loops anyway that you're debugging, right? So anyway, my point is that the GDB is a better way to go. So the problem is it's a little complicated to set up. You have to run the GDB server. You have to pick a port, put it in the background, and then when you launch the debugger, you don't just run GDB, you run Neos2 elf GDB with the elf file. The reason you specify the elf file is that it pulls the debug symbols out of that file. So that way you get the code and the variable names and all that stuff. And then you type target remote localhost with the port number. That'll connect to the debug server. And then you type load to load the program. You can set the breakpoint on main and hit continue, for instance. Load, by the way, resets everything. It loads the ELF file and gets it ready to run. You guys with me? And then you can just use GDB. And it's nice because you can, now the only problem is it doesn't support hardware watch points and it doesn't support the terminal user interface of GDB, if any of you use that. It's all text. Okay, any other questions about that? Okay, so, all right, so once you have all that set up, and we'll help you, we'll answer any questions. The next thing you're going to do is add a parallel I/O, a GPIO in there for the LEDs. You guys have already done this in 3.13. And add a parallel I/O for the keys, right? Now you might say, wait a second, I thought you said we're already using the keys for reset. Well, yes, but that was a direct, using key 0 for reset is handled in your top level wrapper, the Verilog file. If you want to be able to read the keys from your software running on the Neos processor, then you need a parallel I/O peripheral. Does that make sense? Right? In other words, you already have access to the keys through hardware. If you want software access to the keys, you have to add this parallel I/O thing, which, again, you guys have done this already. So in lab 2, in the next lab, we are going to use software to implement pulse width modulation to be able to brighten and dim the LEDs on the board, which is a very common effect. Everything has this now, right? Even like cars. I just bought a new car, and you open the door and all the lights are LEDs, and they just they brighten up and then they dim down, right? All LEDs use this brightening and dimming effect now. You see it everywhere, but it's handled through pulse width modulation, and that can be controlled with software, but it's usually controlled by hardware because controlling PWM is kind of too basic a task for software to be doing, right? But in this class, we're going to be doing both. We're going to do it in hardware or software first and then in hardware, right? When you do stuff like this in software, it's called bit banging, which means that you're writing code. Like we used to have a lab in the old version of this class where we did UART through bit banging. So you would write software on the Arduino to implement a UART channel, right? As opposed to using the hardware. But in this case, we're going to do it for PWM. Okay, any questions? Okay, and so that's what the final system looks like with all the connections. Hopefully there's no bugs in here. I don't believe so. So again, you've got the clock source, the CPU, SD-RAM, the clocks, what is that? Oh, that's the SD-RAM controller, right? Yep. That's the clocks, the PLL. That's the dummy output thing for the SD-RAM clock. UART, LEDs, and keys. These are just GPIO connections. So they allow us to basically go from Avalon to pins, right? What these GPIOs do is they're a bridge. They allow you to do an Avalon read or write transaction over the Avalon bus so that they have a programmed I/O address associated with them, but then they allow you to go straight to pins, right? So these GPIOs are kind of the purest form of software hardware interfacing because, but Avalon means load and store instructions, right? Because it's programmed I/O, and then you go straight to pins, right? And that's the purpose of these guys, is to bridge between the I/O instructions and the actual pins, hardware wires. Now, let me just double check something here. The SD-RAM clocks, so you got the clock. This is the out of phase clock right here. It's called SD-RAM clock. This is a 50 megahertz clock, but it's slightly out of phase from the system clock. Notice how it connects to the clock in on this clock source, so that just kicks it out to the chips, right? But does it also go to the SD-RAM controller? Does it? Yes, it does, yeah. Right. So this SD-RAM clock, I couldn't remember this if this is how we did it. The SD-RAM clock, the out-of-phase 50 megahertz clock, connects to two things, only two things. One is the external pin, so it can go out to the chips. And the other is the actual internal connection for this SD-RAM controller that powers the SD-RAM controller. Okay? Everywhere else, you just use the system clock. Okay? Technically, there's 3 clocks, right? There's the raw unfiltered clock that comes into this guy. There's the raw clock. Then there's the sys clock and the SDRAM clock, which come out of the PLL that are cleaned up, but they're out of phase. Okay? Does that make sense? Okay. I think the rest of this stuff you guys are familiar with already. I have some example code here that blinks the lights, uses the keys and the LEDs in concert to create a little light display. You can use that as like a test bench. And then one final thing we need. Sorry, I almost forgot. So you might be wondering how you implement pulse width modulation in software. Like, how does that work? Because in order for that to work, remember that PWM has a period and a duty cycle, which is based on time, right? So the period is usually in seconds, right? And the duty cycle is in a percentage of the period, right? So 50%. But how can that possibly work? Because the software, how do you measure time in software, right? Well, you use a clock, the system clock. In Linux, you would use the system clock. There's a get time of day function. That's the old way of doing it. There's a newer version of that now called system clock, real-time clock. I forget what it's called now. But basically, there's a function in Linux where you can ask it what the time is. There's a system clock inside the computer. It used to have a granularity of microseconds. Now it's nanoseconds on newer systems. Linux has a much improved version of this now. And of course, I think it's supported by the hardware, the motherboards too. But yeah, there's a system clock. And so you have to be able to refer to that clock. But that's on the motherboard. So how do we don't have a motherboard. I mean, we don't have a system clock on this board. It doesn't exist. So how are we going to keep track of time? Because there's got to be some way to check the clock, to check the time. When I say clock, I don't mean clock signal. I mean clock in terms of the wall clock, right? We need a wall clock time, right? And it has to be very precise in order to control the PWM. So the solution we came up with is to use a performance counter, which is basically it's just a cycle counter, right? So we have a crystal, we have the 50 megahertz clock, and so if we have a counter that just ticks 1 on that counter, we essentially have a clock that has a granularity of 1/50 millionth of a second. That's pretty good, right? The problem is that clock, though, is running in hardware. That doesn't mean the software can keep up to date with it, right? The software can look at it, right? But even if it looks at it as fast as it can, many ticks will go by in between the software's checking of that clock, right? But anyway, we'll have this clock. So we'll add this, there's something called performance counter, and the performance counter was intended to measure performance, but we're not going to use it for that. We're going to use it as a wall clock. We're going to use it as a time reference for the software. So all you have to do is add it. It's just a module. You add it, you make it a slave on the data master, and then you turn it on with this IO write command, and then you read it with these 2 instructions. The clock has to be the counter has to be 64 bits, because if it's only 32 bits and you're adding 1 to it 50 million times a second, it'll actually roll over. The odometer will roll back to 0 after 43 seconds. So you only get 43 seconds worth of counting on 32 bits at 50 megahertz. So unfortunately, you got to use all 64 bits, but the Neos processor is only a 32-bit processor. So obviously, it's going to take multiple operations to formulate a 64-bit value. So, and also the Avalon bus is only 32 bits. So you have to essentially read the lower 32 bits and then the upper 32 bits and then concatenate them together. But the concatenation is kind of only in its software because the registers are still 32 bits in the processor, right? You guys with me? And that's how you do it. Now you might say, wait a minute. What happens if you read the lower part and then you read the upper part and too much time goes by? They'll kind of be out of sync. I don't know. I think that's one of the reasons why you don't necessarily want to do PWM in software, but it works pretty well. You guys with me? Although now I'm remembering, we had a few cases last semester where we had a few groups that had some weird flickering when they did this that we never quite figured out. But in other groups it didn't happen, so I don't know if we ever got to the bottom of that. Okay, but any questions about that? Okay, so that's really all you need for Lab 2. You don't have to do any hardware design for Lab 2. In Lab 3, we're going to do hardware design, and we're going to incorporate it into this platform, right? So you can design some stuff in Verilog and talk to it with software. So speaking of which, let's do a quick review of Verilog. We have a few minutes left. So you guys all took 611, right? You guys still remember Verilog? You're comfortable with that still?
Yeah.
We're not going to be doing anything as complex as what we did in 611, but I'm just going to run through a quick, sorry, that's out of date. I'm going to run through a quick review. So there's VHDL and Verilog. We use Verilog. They're two HDLs. Verilog is designed around the concept of a module because the module allows you to express this design hierarchy. Obviously, we've already seen this even up to this point, because you have the top level lights.sv, and then you've got the Neo system that's one level of the hierarchy under the top level, right? So everything's based around this concept of modules in order to basically simplify a very complex design. That's the whole idea with Verilog. And so you've got Verilog modules, which you write with the module line at the top with the top level IOs. You put the implementation in the middle, and then you put end module, right? So you can have behavioral Verilog, which is where, you guys remember behavioral Verilog? So what constitutes behavioral Verilog? It's basically two things, right? The assign statement, this. So you can assign, which is basically just Boolean algebra, essentially. You can put arithmetic in there too, like multiply and add, and then the compiler will generate an adder circuit or a multiply. You can even put a divide. But when I did this, last time I tried that, it blew up. It used up the whole, I literally just said A divided by B, one line of code, and then it used up the whole FPGA, because I was trying to do a combinational divide, not a pipeline divider and not a multi-cycle divider where hardware can be reused, but a divider that's supposed to be done in one cycle, a divide in one clock cycle. That's death, right? You can't. It's very expensive, right? Because all the shifts and all the subtracts and shifts and restores and all that stuff would have to all be done in a big circuit. But anyway, yeah, there's an assign, but then what's the other piece of behavioral logic that you can put in? You guys remember? The other construct, the other language construct that implies behavioral? It's the always block, right? So there's the assign and always, and that's it. That's really the only behavioral code you can put in. Anything else is a schematic. Like any other Verilog code that you write or read, it's either going to be an assign or an always, which is the leaf nodes, the very lowest level, right? But 99% of the stuff above that is going to be just essentially a structural code, just as basically modules with wires connecting. Most Verilog code you read is just wires, modules with like it's the textual form of a schematic, but it's text as opposed to a drawing, even though every other engineering discipline uses drawings. Civil engineers, they draw stuff. Everything's based on artwork, drawing art, drawing pictures. But in computer engineering, we express things that are more naturally represented as pictures in text, and that's what Verilog is. A lot of it's just structural Verilog. Just because, we like code, because we're kind of computer scientists and kind of engineers. Okay, so anyway, this is an example of behavioral, and this is an example of structural. Structural is where I just instance a module and connect it to the pins. Behavioral is where I do Boolean logic, right? So behavioral is usually only at the lowest levels of the design hierarchy, usually. Make sense? Okay. I like these slides. I forgot about these. So this one is where we mix them, right? So behavioral and structural mixed together in one glob, one module. Is that common? Yeah, kind of. Because like if you need to put a mux in or something, that's behavioral, right? A mux is digital logic, a digital Boolean logic, right? Whereas the stuff connected to the mux is probably going to be other modules, right? So that's structural. So you can mix them together. Okay, and then the other issue that always comes up is this notion of how wires are called different things at different levels of the hierarchy. So this is what I've built here is a NAND gate is my top level. And inside that NAND gate, I'm instancing an AND gate and an inverter, right? So pretty simple, except it's not simple because, for example, the output of the AND gate is called Y inside the AND gate, right? But then inside the NAND gate, which is the top level design, it's not called Y, it's called N1, but it's the same signal. Y inside of here is the same thing as N1 inside of here, which is also the same as A inside the inverter, the input A, right? So this one wire has 3 different names, even in this simple design. This one wire is the same. So if I look at that wire, it will always be the same value, whether I look at it as N1 or as Y or as A, right? That's kind of stinks. Well, the hierarchy is in there to make the design manageable and readable and reusable and debuggable, right? But when you put this on the FPGA, it gets flattened into one mess of it just gets flattened into a big rat's nest of wires, right? And those wires don't have this hierarchy, and so 2 of those names are going to go away, right? You can't have 3 names. Eventually, when you put in the FPGA, it will have a final name that's probably just one of those. I mean, it doesn't have a name at all, technically, but like if you go inside a signal tap and try to tap it with JTAG, it'll just have one name. Okay, all right, and then we use the, you guys remember we use from 611, we use a waveform-based debugging tool for this. I'm going to cover signal tap too, because I think it's going to be needed for lab 3. So this is from a simulator, but like I said, signal tap is a JTAG-based tool that allows you to actually get these kind of waveforms from signals that are actually on the FPGA. Right? So the way it works is the signal tap probe is a RAM, and it has a trigger condition. And when it's like an oscilloscope has a trigger too. You guys ever use an oscilloscope? So like an oscilloscope, generally you set the trigger to be like a rising edge that meets some threshold. So you have a signal and you say, when that signal hits 3 volts, trigger, right? It's the same thing here. You can say, whenever the right enable of this signal is 1, I want you to then start capturing. And it'll capture every cycle until it fills some buffer, however many entries, whatever the depth of that buffer. So you could set it up to like 1024. So you say, whenever right enable is 1, capture 1024 samples, once per cycle. And you capture it, and then it sends out those samples on JTAG, right? And then you'll see them in a waveform. So it's not real time. You're not unlike an oscilloscope, which it's plotting, it's actually keeping pace with the physics, the electricity, the signals. It doesn't do that. It triggers, it captures, and then it offloads the captured data. So you're not seeing a real time, but you're still seeing what was going on when that trigger happened, right? Make sense? So it's a great debugging tool. Now here's the problem. In 611, you would have used that if the simulator worked, if your design worked in the model sim, but didn't work on the FPGA. Then what do? You're done. I mean, there's nothing you can do. You're done unless you have the ability to see what's going on in the FPGA, and that's what you use signal tap for, right? In this class, you can't simulate the Neos processor. Simulation is not even an option. Because, well, technically, there is supposed to be a way you can simulate the Neos processor, but I've never been able to get it to work, despite repeated attempts. Partially, it's because they encrypt it, and it's got to be protected, and you have to jump through hoops. We were never able to get it to work. And frankly, I don't even think it's a great simulation model. I don't think you can actually run like C code through it. I don't think it's that good. I think it's pretty basic, right? So if you want to test hardware, you're going to design hardware. right? But you want to put it in this system with a Neos processor and an Avalon bus and all the other stuff. Simulation is not an option. The only thing you can do to test that is signal tap, right? Which kind of stinks, but there's nothing else to do. So when you guys do the hardware-based pulse width modulator, which is lab 3, if it doesn't work, that's really the only methodology you can use to figure out what's going on. Okay. Okay, and then now this is the other thing too, the always statement. We've got to make sure that you guys are comfortable with this, because we'll have to use this in our modules, especially when it comes to reading the Avalon bus. Why? Because the Avalon bus is a bus protocol like SPI. So if you were writing hardware to be the master or slave in an SPI, you would have to use a state machine. You would have to use sequential logic, because there's different phases of the thing. Like with SPI, there is a phase where you're reading the header packet, right? The header, the first exchange, right? The address and the flags, right? That's a state. Well, there's a state where the bus is idle, right? So if the bus is idle, you're just sitting there waiting for the slave select to go low. Once that happens, then you have to go into a state where you're reading the header. Then you have to go into a state, then you have to count eight cycles, right? And that 8 cycles will then cause you to go to another state where you're reading the data payload, right? So you need to have the ability to use an always statement that uses the clock to create a sequential logic design. Now, we talked about that in 611 at the very end. I don't know if you remember, but at the end of the semester, I had a lecture on state machine design and sequential logic, but we never actually incorporated that into our lab because we just used pipelining. We used pipelining, but we never used a state machine. So we did have always statements to create the pipeline, but we didn't have anything that went into different states, right? So we're going to need that if we start doing bus interfacing with hardware, right? And that's what the always statement does, but not that always statement. That always statement's combinational. These are the always statements, the types that you want, where you say always flip-flop, pause edge clock. So this just creates a flip-flop, but you can do more than just a flip-flop in there. You can have the always statement do more. Here's a better example. Okay, here's a counter. So always flip-flop on the positive edge of the clock. If the reset is high, reset the count. Otherwise, if you're counting up, add 1 to the clock. If you're counting down, decrement 1 from the clock. And this will create a up-down counter. So you're going to need to do something very similar to this if you're going to be generating a pulse width modulation, because it'll be based on clock cycles. If you're counting the number of cycles you want the PWM signal to be high, it's going to be based on a count, right? You guys with me? And then, of course, low is a count. Okay.